welcome to discussion 10 for CS61B. Today we're going to be talking about heaps and hashing. So some announcements first, you can take a look at these when you have time. And let's go into review. So heaps are a special type of tree that follow a few basic rules. So the first basic rule that heaps always follow is that heaps are complete. And what complete means in this context is that the only empty parts of a heap are in the bottom row and to the right. So for instance, in this example that we have right here, this would not be a valid heap if this 8 node, for instance, didn't exist, because we have to fill in our heap row by row from left to right. And the reason we care about this is because it aids us in keeping the heap very bushy and balanced so that the height of the tree is as small as possible, but also so that we can use array to store the contents of the heap. So this would be the first item in the array, second, third, fourth, fifth, sixth, etc., which is a much more condensed way of storing the heap. And to get from, for instance, the root to its first node, you would just multiply by 2. And to get from the root to the second node, you would multiply by 2 plus 1. Same to get from the second node to the fourth and fifth, you multiply by 2 to get 4. And 2 multiply by 2, then add 1 to get to the fifth node, and on like that. So it allows us to store it in a much more condensed way, and it allows our tree to be as short and as fast as possible. The second major property is that in a min heap, every node must be smaller than all of its child nodes. So this is an example of a min heap. And here we see that the 0 is less than both 5 and 1, 5 is less than both 7 and 8, and 1 is less than 2. That's the only rule, is that each parent has to be smaller than both of its child nodes and therefore smaller than all of their child nodes, and etc. And for a max heap, you can just kind of do the exact opposite, where every node has to be larger than both of its children. Keep in mind that this is distinct from a BST. For binary search trees in particular, the left specifically node must be smaller and the right node must be larger, which inherently means that a tree cannot be both a BST and a heap unless there are very, very few, unless there's only 1 or 2 elements in it. So how do you insert into a heap if you want to maintain these properties? Well, when you first insert into a heap, this is a min heap again, you just add it into the next available spot. Again, since we fill out heaps left to right, top to bottom, the next available spot is this one right here. Of course, this isn't the right place, right? We're now breaking that one rule of ours that says that heaps have to, every node in a heap has to be smaller than both of its children. So we do something called bubbling up. So in this case, we compare this node to its parent. So we're comparing -1 and 1. And we notice that 1 is in fact larger than -1, so we just swap them. We keep doing this until we either hit the root, as in this case, or we hit a point where the parent is no longer smaller than the node that we are bubbling up. And once we've done that, as you can see in this last diagram, we've maintained both of our heap rules, it's still complete, and we still follow that min heap property of every node being smaller than both of its children. Deletion works somewhat similarly. So for deletion, let's say in heaps, just as an aside, you can only remove or delete the node at the very top. So in a min heap, you can only get the minimum node, and in a max heap, you can only get the maximum node. Again, these are not like binary search trees where you have access to every single element. Heaps, one of the big use cases for heaps are things like priority queues or queues, where you want to sort things and you only need the thing at the front of the queue. So the only node that we're allowed to delete from the heap is this root node. And so once we delete this one, we take the last element in the heap and we pop it over to just replace that element. So this 4, which was the last element previously, is now where that 0 used to be. Now, naturally, this is in the wrong spot now. So we're gonna have to sync it down. So what syncing down entails is that we compare this node to each of its children and we say, okay, is it smaller than either of its children? And if so, or if it's larger than either of its children, we are going to swap it. So this 4 is bigger than 1, So we're going to swap the two. We have a 1 up here and a 4 down here now. And then again, we're going to swap this 4 and 2. And we're going to end up with a heap that satisfies both our completeness rule and our min heap rule. Moving away from heaps, we're going to talk about hashing. So hash functions are functions that represent an object using an integer. So we use hashes to figure out which bucket in our hash set the item should go in. So we use some sort of function. There's different ways to do this to get this hash function. And then we take the mod of that hash function to figure out which bucket of our hash table it goes in. So you can kind of imagine that this is an example of a hash table. Oops. This is an example of a hash table. And here we have 4 buckets. So let's say these are all of our hashes. And so 4D mod 4 is 0, so that's why it's in the 0 bucket. And 2 mod 4 is 2, 11 mod 4 is 3, etc. So that's how we figure out which bucket it goes into. And inside each bucket, there are different ways to do this, but the usual way that we hash is that we do something called external chaining, which you can see here. And it's essentially having a linked list within each bucket. And in this linked list, we have basically just a list of every item in the bucket. It's unordered. So, in practice, it tends to be in the order of when you added the item, but we don't usually consider this to be any sort of ordered list. When we want to see whether something is in our set, what we do is we take the hash function of the item that we're trying to find, we figure out which bucket it's going to be in, and then we look through that bucket to see if there is an item that equals it. So this is an important distinction. Once we are inside of a bucket, we no longer use the hash code. We use the dot equals function instead to see whether or not two things are the same. And the reason for this is because, well, in Java, there's a very limited number of integers, right? Integers are limited. On the other hand, things like objects, there can be infinite variation. Like if you imagine hashing strings, there's an infinite variation of strings that you can hash. So naturally, some of them are going to hash the same value. So what we do instead is we use dot equals once we get inside. So even if two things have the same hash code, if they're not equal, we won't accidentally say that we have it if we have the wrong item. And because of this, it is vital that your equals function matches the result of comparing hash codes. That is, if two items are equal, their hash codes must be the same. The other way is not true, like two things that are equal, two things that have the same hash code do not necessarily have to be equal. But if you have two items, if you have, like, for instance, two instances of the dog class and you consider them to be equal, then their hash codes have to be the same as well. An alternative to externally change hash maps, which we just talked about, is something called open addressing. So instead of using external chains, whenever there is a collision in whatever bucket you end up in, which is given by h of k, we use another box in our hash. So rather than having multiple things in each box, we are only allowed to have one thing in this box, but whenever a box is filled, we just go to a new box that we figure out through some formula. So an example is something called linear probing, where let's say this is box number 2, and let's say we already have something in there. So we're just going to add some constant m to 2, and then check that box. Let's say m is 3. So now we're going to check box 5. Well, if box 5 also has something in there, now we're going to check box 2 plus 2 times 3, which is going to get us to box 8. And now we check box 8. And so if there isn't something in there already, we're going to put it in there. Otherwise, we're not. And then when we search, we're going to search box h of k and say, okay, is our item in that box already? If the answer is no, then we're going to check box h of k plus m, and etc. until we either come across an empty box, because that tells us that there's no way that it's beyond this, or we hit the end of our hash map. Similarly, there's things called quadratic probing and double hashing, which really follow the same exact process. Quadratic probing, you just multiply instead of adding, and then double hashing, or like you multiply it's a quadratic formula of M, and double hashing, you just have 2 hash code functions for each object, and then you just use that to figure out the next box. Yeah, this is an alternative to open addressing, to externally changed hash maps, but for the most part, I think people mostly use externally changed hash maps. Okay, so that's enough review. Let's get into the worksheet. So just for fun, let's start off looking over the best and worst, or just the worst case runtime for each of these operations. And we're going to do it with and without resizing. So if you remembered, when we use heaps, we are going to use an array notation in order to house them. And so because of that, there is that risk that our arrays, when we add an item or something, that we're not going to have space for it and we're going to have to resize. Similarly to the way that we are resized when we use array lists. So when we do that, our operations are going to take a different amount of time because resizing involves copying over all of the elements from the old array into the new array. So for this case, I will give you a chance to look over this table and collect your thoughts, and then we'll go over it together. Okay, let's go over it. So first, let's talk about insertion without resizing. So this case will be log n like we talked about, because if you recall, as we bubble up, in the worst case, we are only going to be going from a leaf to a root. And as we talked about, one of the benefits of the complete property of heaps is that it's always perfectly balanced and super bushy. So the height of our tree is always going to be log n. Now, with resizing, on the other hand, when we insert an item, we'll have to first copy over all the elements of our heap into a new array, which takes linear time, and then perform the same log n time operation. So that simplifies just to taking linear time because log n is a lower order term. Now when we look about find min, for a min heap, find min will just be us pointing at that top element of the heap. It won't involve any special operations, so it's just constant time. We don't have to move anything around, we don't have to search. The top element of our heap will always be the minimum in a min heap. Similarly, even with resizing, because we're not adding anything, we won't have to worry about our array getting bigger. So it'll still take constant time. For remove min, it'll take log n time, just like we talked about earlier, because again, the worst case is that we sync all the way from a root to a leaf, which takes log n time. And then there's no resizing when you're shrinking the size of the heap, because you're going to have enough space in your array, you'll just have some space left over, and so that'll still take log n time regardless. Okay, so this is our final answer here. So here is kind of a more open-ended question. What are the advantages of using an array-based heap over a pointer-based heap? I'll give you a chance to think about it. Okay, so let's talk about the answer. So pointer-based heaps are less space efficient because, you have to have pointers to different areas in memory, which takes a lot of space to keep track of, right? You need to keep track of both the item and the pointer to each child, versus array-based heaps, you just have them in a line. They're also less time efficient because of things like caching, where an array, based off of the way your computer is cached, it'll kind of take out a huge chunk of the array at a time. So it's usually faster to search through an array, versus pointers, you're gonna have to take things from different areas of memory, so it ends up being a little slower. Now, how can you implement a max heap of integers if you only have access to a min heap? This is kind of an algorithm design question, so I think it's kind of fun. Okay, so I hope you give it a thought. It's okay if you didn't figure it out because it is a little tricky. So in this case, the easiest way to do this, assuming that the min heap that we're referring to here is kind of a black box where you can't modify the insides, is for every insert operation, you just negate the number before you insert it into the min heap, and then when you remove it, you just negate the number that you get back. So basically, you're just flipping the whole number line rather than making any modifications to the heap itself. Kind of clever. Here's another one. So given an array and a min heap, try to describe an algorithm that will allow you to sort the elements of the array in ascending order and then give the best and worst case runtime of your algorithm. I'll give you a chance to think about it. Okay, let's go over it together. So in this case, all you have to do is insert all of your items into the min heap and then call remove min repeatedly to get the items in order from smallest to largest. So let's talk about the worst case first, because I think it's a little easier to conceptualize. So in the worst case, every item being inserted has to bubble all the way up to the root, and all removed items must bubble all the way down. So it takes about log n time per operation, and you have to do this for every single item. So that simplifies to n log n. In the best case, if all items are identical, adding and removing will require no bubbling up or down. So each operation takes constant time because you just have to check once to see whether or not you have to do that initial swap. And since the answer will always be no, it'll just take that one constant time operation. And then we do that operation actually twice, I guess, technically, because you have to first add it, then remove it per item in the array. The total runtime is theta n. So again, this is only the case if all items are identical. If you're not sure why that's the case, I recommend you give it a shot and try drawing out a couple different heaps and see whether any others have this property. But you'll see very quickly that because of the way that adding and removing work, unless all the items are identical, you will inevitably have to bubble up or down, either on the add or the remove. Okay, let's do some assorted heap questions. So describe a way to modify the usual max heap implementation so that finding the minimum element takes constant time without incurring more than a constant amount of additional time and space for the other operations. Now for this problem, I'll give a little hint. It is easiest to do this problem if you kind of think of heaps as not just this abstract concept of a tree, but also as a physical piece of code that we're going to write. It's going to be a class that it has instance variables and instance functions and constructors and things like that. So kind of thinking of it that way might help you come up with more ideas than just thinking of it as an abstract tree. So I'll give you a chance to think about it, then we'll go over it together. Okay, so the key here is to add a variable that just keeps track of the minimum value of the heap. So when we insert a new value, you're simply going to update this variable if the new value is smaller than it. Since the max heap you can only remove the largest element rather than arbitrary elements, that smallest element will only end up being removed when the heap is emptied, right? Because you can only remove the minimum element once you've removed everything above it. And at that point, we'll have to reset the variable keeping track of the minimum value. So all you have to do is have an if statement at the remove max function that just says if this is now empty, if the heap is empty, you can just remove the you can just clear the variable keeping track of the minimum value. Okay, and so now we have a little bit more of a complicated question. So first, there's like 3 parts to this. So first, how do you insert a new element into a D-array heap versus a binary heap? And what is its runtime in terms of D and N? And what is the runtime of finding the minimum element in a D-array heap with N nodes in terms of D and N? And how do you remove the minimum element from a D-array heap? What is its runtime in terms of D and N? So I'll give you a chance to think this through. This is a bit harder, and then we will talk about it together. Okay, so let's talk about this first answer first. So to insert, we're going to do something very similar to what we do in a normal binary heap, in that we are going to add a new element on the last level of the tree and bubble it up. Same exact process of checking with its parent, because again, when you're inserting, the only thing you really care about is whether your parent is greater than or less than you. And since the tree has log D n levels, I think the D is like the base of the log, we have to do at most one comparison per level, and one swap per level. The insertion will end up taking log D n time, which you can simplify as just log n time in the end. So what is the runtime of finding the minimum element? Well, since it's just the roots, just like it is with a binary min heap, all you have to do is check what that root is. So that takes constant time, just like it did before. And then the minimum element, how do you remove it? Again, it's going to be very similar. All we're going to do is do that thing where we take the last element on the last level of the heap and put it in the place of the root and then bubble it down. And at each level, we have to do at most D comparisons where we're checking it with each of the children, and then you have to do one swap. And since there are log D n levels, and removing the minimum takes D log n time, which is distinctly different from the binary heap in a way. It's not that different. The difference was just that before, that D was equal to 2, and so it was like a constant factor that we could just ignore. Now that we don't know what that D is, it's going to be another element of our runtime. Okay, so let's talk about hashing. So our first question is kind of related to hash codes and hash maps. So here we're going to talk about entries, and then just for context, an entry in this context refers to a key value pair. So inside hash maps have these entries within their external chains, and they are sorted by their key. So that's why the entry has to contain both the key and the value, so that when you do dot equals, you can compare against the key, and then you can retrieve the value. So the two questions are, if you modify the key that has been inserted into the hash map, so you modify the instance of the key that is currently present within the entry, can you still retrieve that entry? And likewise, if you modify the value, the instance of the value that has been inserted into the hash map, can you retrieve that entry? So you can kind of assume that we know we're looking for that modified key, so we have the modified key as well in our hand when we're looking through these things. So I'll give you a chance to think about it, and then we'll go over it together. Okay, let's go. So this first one is sometimes, and the reason is because although we have that new key, and so dot equals will still return the same value, our entry is now could be in the wrong bucket, right? So if the hash code changed when we changed our key, then we will be looking for a different bucket for our key, and we will not be able to find it. If we're lucky and both keys hash to the same bucket, then we will be able to go through and we'll be able to find it. But again, there's no way we can guarantee that. For the value, it's actually always, and the reason is because entries are completely indexed and found based on the key, not the value. So altering the value basically has no impact on whether or not we can find our entry. Okay, so let's talk a little bit more about hash codes. So we're going to explain whether each of the following hash codes are valid or invalid. So just as a refresher, there are kind of two different axes upon which you can think of hash codes. So the first is valid or invalid. Invalid hash codes, for instance, they return they're non-deterministic, which means that they don't return the same value every time you call them, which, if you could think about it, would naturally make it impossible to use it for like hashing or hash sets or anything, because you would end up with getting a different value every time. And then similarly, an invalid hash code is one where the dot equals function, two things that are equal, do not return the same hash code, because that violates the whole point of hash codes. But for valid hash codes, they can also be good or bad. So like we talked about, good hash codes, the goal is to minimize collisions. So we don't want lots of things hashing to the same value, because then our hash table will have a lot of things in the same bucket, and it'll essentially end up being a linked list that takes linear time to find something, rather than a hash table that takes about constant time to find something. So the goal is to minimize collisions, and so a bad hash code has lots of collisions, and a good hash code has very little collision. So I'll give you a chance to look at each of these hash codes and tell me whether they're valid or invalid, or good and bad, and then we will talk about it together. Okay, let's go. So for this first one, it is valid, but it's bad. So in this case, it satisfies our two requirements in that it is deterministic. So it always returns -1 for the same object. So that means, you'll be able to look at the same bucket twice. And it does return the same value if two items are equal to each other. Again, that's good. However, it's not a very good hash code because every single object hashes to the same value, which will inevitably result in you having lots of collisions and your runtime being pretty bad. Now, number 2 is valid, and it's a better hash code. So again, it's deterministic. It returns the same value if the int value is the same, and it satisfies that equals function. But even though it's a better hash code, it would have been even better if they just didn't square it, because now positive and negative numbers are going to collide when they otherwise wouldn't have. So it's kind of unnecessary to do that, and it increases the number of collisions. Now our next hash code is invalid, and this is because there is a random element here. It'll return a random integer, so the first time you hash this, you might get 5, and then the second time you might get 8, and that'll result in you looking in the wrong bucket for your key in the future. So this is an invalid hash code. It doesn't satisfy that deterministic requirement. And lastly, this hash code is a little harder, but it is also invalid, and the reason is because as the worksheet I believe says, hash codes, so that in this specific object, two things are equal if they have the same int value, and super.hashcode actually just returns the exact memory address of this object. And so two items that have the same int value might be stored in two different places in memory if they're two different instances, and therefore you'll have a hash code that's different even though those two items are equal. And that makes this invalid. Okay. And lastly, let's go over some hashing practice. So we are given a list of terms, I think fruit, and we are going to try to hash them. And we also have a load factor here. So whenever the load factor, I believe, is like 2 or something, we are going to have to increase the size of our hash table to keep everything nice and spread out. So I'll give you a chance to look at it, and then we'll go over it together. Okay. Let's go over this. So the first thing we're adding is apple. Again, I think we're hashing based off of the first letter, and A is going to hash to 0 here. And then the thing we're adding next is cherry, which is going to go down here because cherry hashes to 2, and then we put it in the second box. And then fig goes over here, guava goes over there. And now when we add our next thing, we're going to face the issue of load factor, right? So now there's 4 items and we have 4 boxes. At this point, we have to increase the size of our hash table. So now we have to first reanalyze everything. So if you notice, adding all of these things took basically constant time, but how to do this, we have to go through every element, and things like fig and guava have to be moved to their new position. So this is going to take longer than the other additions that we made. But now we can add durian in its place, and then we're going to add apricot, and then banana, and that brings us to our final result for this hash table. Okay, well, that brings us to the end of the worksheet today. I hope you guys have a great week, and I'll see you guys next week. Bye!